Hello everyone, welcome to this lesson. So in this lesson we're going to go through a new series which are ordinary differential equations, or the solving of ordinary differential equations. So what does it mean to solve an ordinary differential equation? Well, in some instances you know how a function is changing. In other words, you have a derivative of the function, which in this case we have the derivative dy dx and is equal to 2y, which means you know how the function is changing in relative to the derivative. So here the derivative is 2 times the function value, but you don't know what the y is, you don't know what the function is, and you also have an initial condition, which means you know that the function at x equals 0 is equal to 1. So with only these two pieces of information, what solving ordinary differential equation gives you the power to do is to actually trace out the y, trace out the original function. And it does that in multiple ways that we're going to be going through in this series. In this lesson, we're going to be doing that using Euler's method. So the exact solution here for this derivative is actually e to the 2x. So what we're going to be doing, we're going to be using this equation here, Euler's method, which is defined as yi plus 1 is equal to yi plus phi, which is basically a derivative at yi multiplied by h. And you can see this is actually very simply a linear extrapolation. So you're taking information at yi, which is basically yi and the derivative at that point, and extrapolating linearly what the y at yi plus 1 might be. And basically you're going to be taking this point, information at this point, linear extrapolate to what this point might be, then take the information at this point, linear extrapolate what this point might be, and keep doing it, and you're going to eventually trace out what the original function is, or what the exact solution for this derivative is. So let's actually see this for multiple step sizes. So here we're going to be dealing with Euler's method at a step size of 0.5. So what do I mean by a step size of 0.5? The step size tells you the number of estimations that you're going to be getting in a certain interval. In other words, if I'm dealing with an interval from 0 to 1, and I'm dealing with a step size of 0.5, that means I'm going to be using this initial condition to get my first estimate at 0.5 and then my second estimate at 1. And you can predict that if I'm going to be using a step size of 0.2, for instance, I'm going to be getting an estimation every 0.2 step size, which means I'm going to be using this information to get a estimation of 0.2, then 0.4, 0.6, 0.8, and 1. And we're going to be seeing later in this lesson if changing the step size has any effect on the accuracy of tracing out this function. So let's actually see how this works. So we're going to take this information at this initial point that we have here, which is y naught is equal to 1. So basically y is 1 at x equals 0. So we're going to be using this equation here, Euler's method, to figure out what the estimated y value is at 0.5. So we're going to know, we know that yi here, or y naught, is 1. We're going to add to it this phi, which we know is the derivative at yi, and we have an equation for the derivative here. So it's basically 2 multiplied by y, and we know here y is 1. So basically 2 multiplied by 1 is 2, and multiplied by a step size that we have here is 0.5. So we have 1 plus 1, so 2. So Euler's method estimates y equal 2 at x equal 0.5. So now we're going to take information that we have here, which is the 2 that we just calculated, to estimate what the y is at 1, at x equal 1. So we're going to be using the same equation. So we're going to say y2 is equal to, and we know that y here is 2. We're going to add to it the derivative at this point, and we're going to be again using this derivative to calculate it. So it's 2 multiplied by 2, so that's 4. 4 multiplied by half, so that's 2. So we have 2 plus 2 is equal to 4. So Euler's method estimates y to be equal to 4 at x equal 1. Now you can see from this equation here that the true value at 0.5 is 2.72, and Euler's method actually estimates it at 2, so you can actually see that we have incurred a little bit of error here. And here the true value is 7.39, and Euler's method estimates it at 4, so we have a lot of error here. So why do we have actually a lot of error in the second estimation as the first one? Remember, this is a linear extrapolation. So from 0 to 0.5 here, this function is closer to linearity than from 0.5 to 1. So we have more curvature from 0.5 to 1 than we have from 0 to 0.5, which is why we had so much error in this second interval as we did in this first interval. So you can actually see a lot of the error that comes from the Euler's method is because of the assumption of linearity. So let's actually see what will happen if we actually upped the step size to say 0.2 or 0.1. So if I up the step size to say 0.2, let's examine 0.2. So 0.2 meaning that we're going to get a y estimate every 0.2 increment. So we have 0, 0.2, 0.4, 0.6, 0.8, and 1. So if you can see from this graph here, and the estimate that we're dealing with right now is at 0.2, so it's the blue. And you can see that at 0.2, it's actually very, very close to the true value, which is the orange line here. And you can see from the table here that Euler's method, basically what we've done in the previous slide, have estimated the y at 0.2 as 1.4 and the true value is 1.49. So it's actually relatively close estimation. Now, if we go to the 0.4, you can find that we have 1.96 and the true value is 2.23. And if we go to 0.6, we have 2.744, 3.32. So you can actually see that the gap between the true value and the approximation keeps getting wider and wider. If we go to 0.8, now we have 3.8416. And the true value is 4.95. And finally 1, which is here, this gap that we have here, this one is 5.37824, and this one is 7.39. Now, if you can see, why is the distance between the approximation and true value increasing as we're moving? Again, much like with the 0.5, because as we're moving with this function, the curvature increases with each interval. But you can also notice that because we made the interval smaller, the estimation interval smaller, instead of 0.5, we made it 0.2, we have kind of subsided the effect of the curvature on this equation. So you can see that the blue actually gave a better approximation for this function than the yellow did. So both of them capture the trend of the original exact solution, but not necessarily the true value. So let's actually see what's going to happen if we actually even reduce the step size to 0.1. So if I reduce the step size to 0.1, so you can see this is the gray. So you can actually, from the graph, see that it's going to actually give a better estimation. Again, because a smaller interval subsides the effect of the curvature, giving us better approximations. And you can see here, so if we look at, say, 0.2, when I'm using a step size of 0.1, it estimated at 1.44. Here estimated at 1.4, so 1.44 is actually closer to the true value at 1.49. So reducing the step size by 0.1 have actually made the solution more accurate at 0.2. What about 0.4? So 0.4 here is 2.074. In 0.2 was 1.96. So actually reducing the step size actually made the approximation of 0.4 actually more accurate. And you're going to find the same thing with 0.6. Here we have 2.986. Here is 2.744. So this one is actually closer to the true value as well. This is 4.3. This is 3.8. So even closer. And this one is 6.19, which is much better of approximation than 5.37824. So what have we learned in this lesson? So in this lesson, we have introduced ordinary differential equations, we have also introduced the first, a very simple technique, which is Euler's method, which is merely a linear extrapolation. You take one point and the information of it, the y value and its derivative, and extrapolate the next point. The next point that you estimate depends on the step size that you use, and we examined the step size of 0.5, so we got from 0 to 0.5 to 1. Then we also examined 0.2 and 0.1, and we found out, especially with functions that have a lot of curvature, reducing the step size reduces the effect of the curvature on the linear extrapolation, and you actually get better estimations for the value. Again, with ordinary differential equations, you only have a differential equation. So if you know how the function is changing and you have an initial condition, you can use Euler's method, a linear extrapolation method, to actually trace out what the exact solution is for that particular derivative. So very, very simple technique, very effective technique. And in the next lessons, we're going to be going to multiple more methods of how to trace out the function value more accurately. So that's it for this lesson, and I will see you in the next lesson.